In this video, we are going to talk about limits and how to determine the limit of a function. So let f be a function that is defined for all values of x as x approaches a but not equal to a, and let a be a real number or infinity. Now, as x gets closer and closer to a, the function approaches a limit L, so that the limits of that function, that is the limit of f of x as x approaches a, is equal to L. So L is the limit of the function as x approaches a. Now, in finding the limit of a function, the function does not necessarily need to be defined when x is equal to a. Now, what really matters is how the function is defined as x approaches a, or better still, as x gets closer and even more closer to a. Now, before we start solving some examples, first of all, let's consider some of the basic properties or theorems of limits. Now, if the limit of f of x as x approaches a is equal to L1, and the limit of g of x as x approaches a is equal to L2, then the limit of f of x plus or minus g of x as x approaches a is equal to, now we can split this to have the limit of f of x as x approaches a plus or minus the limit of g of x as x approaches a. Now this is equal to L1, and then we have plus or minus L2. 2. The limit of c times f of x as x approaches a is equal to, now we can pull c out so that we have c times the limit of f of x as x approaches a. The limit of f of x as x approaches a is L1, therefore we have c L1. 3. The limit of a constant function as x approaches a is equal to the constant. Now c here is the constant, so the limit of c as x approaches a is equal to c. 4. The limit of f of x times g of x as x approaches a is equal to, we can have the limit of f of x as x approaches a times the limit of g of x as x approaches a, and this is equal to L1 times L2. 5. The limit of f of x divided by g of x as x approaches a is equal to, now we can have the numerator to be the limit of f of x as x approaches a divided by the limit of g of x as x approaches a, and that is equal to L1 divided by L2, where the value of L2 is not equal to 0. 6. the limit of f exponent n of x as x approaches a is equal to the limit of f of x as x approaches a, all exponent n. Now we have what's in the brackets to be equal to L1. Therefore, that is equal to L1 exponent n. And then 7. The limit of the nth root of f of x as x approaches a is equal to the nth root of the limit of f of x as x approaches a, and that is equal to the nth root of L1. So these are some of the basic properties or theorems of limits, and we are going to use these properties to solve a couple of examples. So let's try these examples. We are going to find the limits of the following functions. Starting from example A, that is the limit of 5x as x approaches 2. Now we can think of this limit as pulling out 5 because 5 is a constant, so we can pull out 5 so that we have 5 times the limit of x as x approaches 2. Now directly substituting 2 into this limit, we have 5 times 2, and that is equal to 10. Now so long as you want to substitute what x is approaching into this limit, the limit goes away. So the limit of 5x as x approaches 2 is equal to 10. Now let's move on to B. That is the limit of x cubed plus 1 as x approaches 10. Now we can express this as the limit of x cubed as x approaches 10 plus the limit of 1 as x approaches 10. So for this term, we can directly substitute 10 into this limit so that we have 10 cubed, or better still, we can express that as the limit of x as x approaches 10 all cube. And then for the limit of 1 as x approaches 10, 1 is a constant, and therefore the limit of a constant function is equal to the constant itself, so that is equal to 1. So we are going to directly substitute 10 into this limit so that we have 10 exponent 3 plus 1. Now 10 cubed is 1000, and then plus 1, and that is equal to 1001. Now to see, we have the limit of 5 divided by x squared as x approaches 4. So this can also be thought of as the limit of 5 as x approaches 4 divided by the limit of x squared as x approaches 4. We can further represent this as the limit of x as x approaches 4 all square. Now the numerator is a constant function, therefore the limit of 5 as x approaches 4 is still 5, and then we substitute 4 into this limit, that is 4 square, and 4 square is 16, so we have the limit to be 5 over 16. D, we have the limit of the cube root of x as x approaches 8. So we can express this as the cube root of the limit of x as x approaches 8, and that is equal to the cube root of 8. Now 8 can be expressed as 2 exponent 3 And the cube root can also be expressed as everything here exponent 1 over 3. So that is equal to, we have 3 cancelling out 3, and then we are left with 2 exponent 1, which is equal to 2. Therefore, the limit of the cube root of x as x approaches 8 is equal to 2. Now let's consider some more complex examples. So how do we find the limits of the function x squared plus 3x minus 4 divided by x squared minus 1 as x approaches 1? Now let's try to substitute 1 into this limit. So we have 1 square plus 3 times 1 minus 4 divided by 1 square minus 1. 1 square is 1, 3 times 1 is 3, minus 4 divided by 1 minus 1 is 0. 1 plus 3 is 4, 4 minus 4 is also 0. So we have 0 divided by 0. Now 0 over 0 is indeterminate because we don't know what 0 over 0 is. So instead of plugging in 1 into this limit, we can think of finding the factors of both the numerator and the denominator to see if any of the factors will be the same so that we can cancel out those factors. So for the numerator, we have the expression x squared plus 3x minus 4. Now the coefficient of x squared is 1, the coefficient of the constant is negative 4. So 1 times negative 4 is equal to negative 4. Now we need to find the factors of negative 4 such that when you multiply them, you have negative 4. However, when you add them, you have plus 3. So factors of 4, we have 1, 4, 2, 2. Now since we are looking for the factors of negative 4, that will give us plus 3 when we add them. Then we can think of negative 1 plus 4. So we are going to use this pair, negative 1 and then plus 4. So we have the limit of x squared plus 3x minus 4 being x minus 1, x plus 4 divided by, now for x squared minus 1, that is a difference of 2 squares. So we can express this as x squared minus 1 square. So that will be equal to x minus 1, x plus 1. So we have this to be x minus 1, x plus 1 as x approaches 1. Now we have x minus 1, x minus 1. So let's cancel them out. And therefore we have the limits of x plus 4 divided by x plus 1 as x approaches 1. Now at this point, we can directly plug in 1 into this limit. So that's going to be 1 plus 4 divided by 1 plus 1. Now 1 plus 4 is 5. And then 1 plus 1 is 2. Therefore, the limit of this function as x approaches 1 is equal to 5 over 2. Now let's solve question 2. That is the limits of the square root of x plus 2 minus 2 divided by x minus 2 as x approaches 2. Now substituting or plugging in 2 directly into this limit means that we are going to get 0 over 0, which is indeterminate. Now to find the limit of this function, the best thing to do is to rationalize this function. Now we have the numerator to be a set, that is the square root of x plus 2 minus 2. Now this is a set, so we need to rationalize this set in order to find the limits as x approaches 2 of this function. Now let's consider f of x to be the square root of x plus 2 minus 2 divided by x minus 2. And let's try to rationalize this function. Now, because the numerator is a set, we are going to multiply both the numerator and the denominator by the conjugate of the numerator. So the conjugate of the numerator becomes the square root of x plus 2, and then subtraction sign changes to addition sign. So we have plus 2, and then we do same for the denominator, the square root of x plus 2 plus 2. Now let's simplify this. So we are going to multiply across. Now, square root of x plus 2 times square root of x plus 2 is equal to x plus 2. That is, if you have the square root of a times the square root of a, that is equal to the square root of a square. Square cancels square roots. We have a. So that is square root of x plus 2 plus square root of x plus 2 is equal to x plus 2. Now we have square root of x plus 2 times 2. That is 2 times the square root of x plus 2. Next, we have negative 2 times square root of x plus 2. That is negative 2 times square root of x plus 2. And then negative 2 times 2 is negative 4. So we have this all divided by x times square root of x plus 2. That is x times square root of x plus 2. X times 2 is 2x. Negative 2 times square root of x plus 2. That is negative 2 square root of x plus 2. And then negative 2 times 2 is negative 4. Now let's simplify further. So 2 roots x plus 2 minus 2 roots x plus 2 goes to 0. So they both cancel each other, and we are left with x plus 2 minus 4. Now 2 minus 4 is negative 2. So we have x minus 2 divided by. Now looking at the denominator, you realize that the square root of x plus 2 is common to both x and then negative 2. So we can factor out the square root of x plus 2, and then we have inside of the bracket x minus 2, and then we have plus 2x minus 4. Now don't forget that 2x minus 4 can also be expressed as 2 into brackets x minus 2. So instead of writing 2x minus 4, we are going to write 2 into brackets x minus 2. Now x minus 2 is common to both 2 and then square root of x plus 2. So we can factor out x minus 2, and then we have inside of the brackets we have the square root of x plus 2 plus 2. Now x minus 2 cancels out x minus 2, and then we are left with 1 over the square root of x plus 2 plus 2. So this is the simplified form of f of x. Now in that case, the limit of this function can be reduced as the limit of 1 over the square root of x plus 2 plus 2 as x approaches 2. At this point, we can directly substitute 2 into this limit. So we have 1 over square root of 2 plus 2 plus 2. Now 2 plus 2 is 4. So we have square root of 4 plus 2. Square root of 4 is 2. Therefore 1 over 2 plus 2, and that is equal to 1 over 4. Therefore the limit of this function as x approaches 2 is equal to 1 over 4. Now let's move on as we solve some more examples. Now to question 3. Let's find the limits of the function x minus 4 divided by the square root of x minus 2 as x approaches 4. Now let's consider x minus 4 divided by the square root of x minus 2 to be f of x. And let's try to simplify f of x. So we have f of x equals x minus 4 divided by the square root of x minus 2. Now you realize that the denominator is a set. So we need to rationalize this function, or rationalize the denominator of this function. So we multiply both the numerator and the denominator by the conjugate of the denominator. So that's going to be square root of x, and then this changes to plus, so plus 2, and then we have same for the denominator. Now let's try to multiply across. Now x times square root of x is x root x. X times 2 is 2x. Negative 4 times square root of x is negative 4 root x. And then negative 4 times 2 is negative 8. Divided by root x times root x is x. Root x times 2 is 2 root x. Negative 2 times root x is negative 2 root x, and then negative 2 times 2 is negative 4. Now let's simplify further. You realize that square root of x is common to negative 4 as well as x. So we factor out square root of x, and then we have x minus 4, and then plus 2x minus 8. We can as well factor 2 out, so that we have x minus 4, all divided by 2 root x cancels out 2 root x. We are left with x minus 4. Now from the numerator, we have x minus 4 that is common to each of the terms, and then inside of the bracket we have square root of x plus 2 divided by x minus 4. So we cancel out x minus 4, and then we have f of x as the square root of x plus 2. Therefore, the limit of x minus 4 divided by the square root of x minus 2 as x approaches 4 reduces to the limit of the square root of x plus 2 as x approaches 4. Now we substitute 4 into this limit. We have square root of 4 plus 2. Now square root of 4 is 2. Therefore, 2 plus 2 is equal to 4. Therefore, the limit of this function as x approaches 4 is equal to 4. Now to the last question for today's lesson. How do we find the limits of the function x divided by the square root of 1 plus x squared minus 1 as x approaches 0? Now the denominator is a set, so we are going to rationalize this function, that is multiplying both the numerator and the denominator by the conjugate of the denominator. So let f of x be equal to x over the square root of 1 plus x squared minus 1. Therefore we have f of x equals x over the square root of 1 plus x squared minus 1. We multiply both the numerator and the denominator by the conjugate of the denominator. Now let's simplify this. Let's multiply across. So we have x times the square root of 1 plus x squared, which is x times square root of 1 plus x squared, and then 1 times x, or better still x times 1 is x. We have this divided by the square root of 1 plus x squared times square root of 1 plus x squared gives 1 plus x squared, and then square root of 1 plus x squared times 1 is the square root of 1 plus x squared. Negative 1 times square root of 1 plus x squared is negative square root of 1 plus x squared, and then negative 1 times 1 is negative 1. Let's simplify further. Now from these two terms, x is common to both terms, so we factor out x, and then we have square root of 1 plus x squared plus 1, all divided by square root of 1 plus x squared minus square root of 1 plus x squared goes to 0. So we are left with 1 plus x squared minus 1. Now 1 minus 1 is 0, so we have only x squared. At this point, x cancels out one of the x's here, and then we have the square root of 1 plus x squared plus 1 divided by x. So that is f of x. Therefore, we have the limit of this function to be now the limit of the square root of 1 plus x squared plus 1, all divided by x as x approaches 0. Now at this point, we still have the denominator to be x. Now if we should plug in 0 in this limit, then we are going to have the square root of 1 plus 0 squared plus 1 divided by 0, and that will be equal to square root of 1 plus 0 squared is square root of 1, which is still 1, and therefore 1 plus 1 is 2. So we are going to have 2 divided by 0, and then 2 over 0 is also undefined. So what then is the limit of this function as x approaches 0? Now if you have a function f of x which is equal to p of x divided by k of x, where k of x is not equal to 0, and the limits of p of x as x approaches a is equal to L1, and the limit of k of x as x approaches a is equal to 0, then it means that the general limit of that function does not exist. And that is exactly the case for this function. Now the limit of the numerator is 2 and the limit of the denominator is 0. Therefore we say that the limit or the general limit of this function does not exist. Now in the subsequent lessons, we are going to consider whether the limit of a function exists or not. Now under that lesson, we are going to consider the left hand limit and the right hand limit. Now if the left hand limit is not equal to the right hand limit, it means that the general limit of that function does not exist. Now that is exactly the same case we have here. The left hand limit of this function is not equal to the right hand limit of this function. Therefore we say that the general limit of this function does not exist.